Welcome once again friends in this spoken tutorial on transformer part 2. In this spoken tutorial we will see the working principle and the working of the transformer. So on what principle does the transformer works? In one sentence we can say that the transformer works on principle of mutual induction. And how does it give the output voltage when input voltage is given to the primary winding? When the AC supply is given to the primary winding, it produces alternating magnetic flux in the core. Since both windings are wound on the same core, this flux produced by primary links with both the windings, that is primary and secondary. This alternating flux, because it is changing, it changes the flux linkages of primary and secondary winding, and as per the Faraday's laws of electromagnetic induction, EMF is induced in both primary and secondary winding. Now, this EMF induced in primary winding is of self-induction type, whereas the EMF induced in secondary winding is mutually induced EMF. Since the EMF at the output, that is a secondary winding, is mutually induced EMF, the transformer is said to work on the principle of mutual induction. Now, how much EMF is induced in either primary or secondary winding? So that is what we want, an EMF equation of the transformer. Ideally, if we neglect the leakage, same flux links with primary and secondary both, because it is confined in the core, and due to this, EMF induced in single turn of both windings will be same. The EMF induced in a winding depends upon maximum value of flux phi m or flux density Bm in the core, the supply frequency of in hertz, and number of turns of the winding. Thus, the EMF induced in primary and secondary winding respectively are given by E1 is equal to 4.44 phi m into F into N1, and in secondary E2 is equal to 4.44 phi m into F into N2, where flux phi m, maximum value of flux phi m, can be given as Bm into A, that is, Bm is the maximum value of flux density in the core. N1 and N2 are the number of turns of primary and secondary winding. Bm is the maximum value of flux density in the core. A is the cross-sectional area of the core in meter square. So what is meant by transformation ratio of the transformer? The transformation ratio of the transformer is the ratio of induced EMF in secondary winding to the induced EMF in primary winding. It is denoted by K and is given by E2 upon E1. For K is greater than 1, E2 will be greater than E1 and it's called as step up transformer. If K is less than 1, E2 will be less than E1 and it's called as step down transformer, whereas K is equal to 1, it is called as 1-to-1 transformer. Step up transformer is used to increase the voltage level from primary to secondary. Step down transformer is used to decrease the voltage from primary to secondary, whereas 1-to-1 transformers are used as isolation transformers. From EMF equation in last slide, we can say, right, K is equal to E2 by E1, which will be equal to N2 by N1. Its transformation ratio is equal to the turns ratio of the transformer. Now, what's ideal transformer and a practical transformer? Though ideal transformer cannot be realized in practice, we will see what is meant by ideal transformer. It has no winding resistances, windings are ideal, core is ideal, so there is no leakage of the fluxes in the core, and therefore leakage reactance of the winding is 0. The core has an infinite permeability, so reluctance of the core is 0 and negligible current is required to establish the magnetic flux in the core, and no losses in the core, that is hysteresis loss and eddy current loss is 0. So this is what are the properties of ideal transformer. So these properties result in applied primary voltage and the induced EMF in primary V1 and E1 equal, secondary induced EMF E2 equal to secondary terminal voltage V2, and primary apparent power is equal to secondary apparent power. This can be written as V1 is equal to E1, V2 is equal to E2, and V1 I1 is equal to V2 I2. Therefore, from EMF equation again and above relations, we can write K is equal to E2 upon E1, V2 upon V1, N2 upon N1, which is equal to I1 upon I2. Now let's see what's the difference between practical and ideal transformer. Here the windings are practical and therefore possess the resistance, and therefore voltages will not be equal. Leakage fluxes exist in the practical transformer and therefore windings possess the leakage reactances. Core does not have infinite permeability, they have finite permeability, and therefore reluctance of the core is appreciable. Magnetization current will be required to establish the magnetic flux, and hysteresis and eddy current losses occur in the core which are absent in ideal transformer. Now for above properties result in following: applied primary voltage will be greater than primary induced EMF. Secondary induced EMF will be greater than secondary terminal voltage. Primary apparent power will be greater than secondary apparent power. This can be written as V1 greater than E1, E2 greater than V2, and V1 I1 greater than V2 I2. Therefore, in case of practical transformer, though K is equal to E2 upon E1 and N2 upon N1, it is not exactly equal to V2 upon V1 or I1 upon I2. That's approximate relationship, approximately equal to V2 upon V1 or I1 upon I2. Though this is true for finding the value of K for practical transformer, V1 and V2 are taken as the rated values specified by the manufacturer. Let's have some practice about the formula that is written for EMF equation. Here, a single phase 50 Hz transformer is given with 100 cm square cross sectional area and working flux density of 1.2 in the core. Number of turns of primary and secondary are given 800 and 400 respectively, and we are asked to determine the EMF induced in primary and secondary winding and transformation ratio. So writing the given data and writing the relations that we have, Im is equal to Bm into A, E1 is equal to 4.445 m into F into N1, and E2 is equal to 4.445 m into F into N2. Substituting the values, we get E1 is equal to 2133.12 and E2 is equal to 1066.56, and the transformation ratio, which can be found either by E2 upon E1 or N2 upon N1, we get it to be 0.5. Now friends, let's have practice with this one. These are the practice problems you have to solve. Answers are given. Tally the answers after solving. Thank you. We'll see you in the next spoken tutorial.